All right, here we go. Our first example of volumes by cross-section. From 2000, this is from test AB. I don't remember if AB and BC shared this problem. Remember earlier in an earlier video, I referenced the fact that some of the questions are in common or shared between AB and BC. I don't remember if this was also on the BC test, but it definitely was on the AB in the year 2000. That was 24 years ago. Here in question number one. So let's see what the prompt is. R is the shaded region. Let R be the shaded region in the first quadrant, enclosed by the graphs y equals e to the negative x squared, y equals 1 minus cosine x, and the y-axis, as shown in the figure below. The region R is the base of a solid. For this solid, each cross-section is perpendicular to the x-axis and is a square. Find the volume of the solid. Okay, for this solid, each cross-section is perpendicular to the x-axis is a square. Each cross-section perpendicular. Okay, so this is important because it tells me that we're going to make our slices in this direction. Now, you can see they're not the same shape, right? If I were to take a slice here, this would be smaller than a slice here, which would be smaller than a slice here. I'm just showing you where I would slice it and how I would slice it. All right, what do we know? We know that the shape is a square. So I'm going to come over here and I'm going to say, how do I find the area of a square? Well, the area of a square is just take a side and square it, right? Pretty straightforward. So the area of a square in terms of a geometric shape, just take a side, an edge, and square it. But if you think about it, this is the base of the square. The square is actually like going up. I know that's not a very good drawing, but it's jetting up out of the page, right? And if that's the case, that means this blue length is the side of a square. So whatever this length is, that's the side of the square. So if I can find an equation for that, then I'm good. Because the next step, so this is step one, figure out what formula we're going to use. Step two, let's write an area function. So this tells me what I need to find. Oh, I need to find this. But because my blue lengths are going to be different, I need to build a function depending on what x value I'm on. And that's going to require me to create a function. Now, how do I do this? Well, how do I find the length? If you recall, when we were doing area between curves and we were doing these little skinny rectangles, well, the length of the rectangle, top minus bottom, right? That's how you find a vertical length. Whatever the top y value is minus whatever the bottom y value is. Well, the top function is e to the negative x squared minus the bottom function is 1 minus cosine x, and then I'm going to square that. So maybe I should do this in a different color here so that you can see how I'm getting this in case you're wondering. This is my top function, so that's going to go first, minus this is my bottom function. This one is my bottom function, so that's going to go second. Notice how I'm putting it in parentheses because I have two terms and I'm subtracting. I guess I could also write it as minus 1 plus cosine x. You could write it that way and simplify it a little bit. But I'm just going to put them in there the way they're written so that you can see how I set this up. So what does this expression do for us? This expression, depending on what x value I'm on, so if I want to find the area of the square slice, of the square slice at 0.5, if I substitute 0.5 in here and 0.5 in here and do all of this business, it's going to find the area of that square. But what we want to do is we want to add an infinite number of square slices. This function tells us how to find the area of each of those. But in order to do that, we need the integral. And so here we go to step three. Step three says to find the volume of the function, we're going to need the integral of this thing. So I'm going to take this whole thing and I'm going to say, oh, e to the negative x squared minus 1 plus cosine x. Now I am getting rid of those inside parentheses. Squared dx. Why is there a dx there? Well, because if you think about it, those slices, even though they're really, really thin, are looking like this. They're squares, right? But they're really, really slices like that. And so this little width, that's my delta x, that would be dx right there. So this square is sitting right here, and it's kind of jetting out, pointing, rising out of the paper. And that's what we're seeing. Now, here's the dealio. The last part, I got to find out where to start and where to end. So where does my shading begin? This is my shading. This is my region. Where does it begin and where does it end? Since I'm looking for dx, everything's in perpendicular to the x, I need x values. So it starts at 0 and it ends at, oh, does it end at 1? Question mark? I got to be very careful there. And so I'm going to go to my calculator. I'm going to graph these two equations, and I'm going to see if they actually intersect at 1, because if they don't, I actually need the intersection point. I can't round it to say, oh, it looks like it's about 1. I have to figure it out. And so I go to my calculator, and let's see if we can get that going here. Okay, so I'm going to go to y equals. Let's get rid of that, and let's type in what we want. So we want e to the negative x squared, to the negative x squared. And then the other one is 1 minus cosine x. 1 minus cosine x. Close. And I want to open the window. Remember, this is only in the first quadrant, so I'm going to start at 0. And by looking at this, it doesn't look like I have to go very far, from 0 to 2. And then on the y-axis, I think I'm going to go 0 to 2 as well. And graph. There's the first curve. Oh, I think I am not in. Oh, look at this. Somebody reset my calculator to degrees. So I need to go back to mode and make sure that I'm in radian. Now when I graph it, there's the first curve. There's a second curve. And now I can see, oh, maybe it's not 1, is it? So how do we find an intersection point? Second trace. Let's do the intersection point, intersection option, number 5. And we're going to move closer and closer and closer, I think. And it's telling you, is this blue equation one of the curves you want to find the intersection for? Yes. Is this red equation the second function you want to find the intersection for? Yes. I don't want to take a guess. So my intersection point is actually at 0.9419. I'm going to put 4 decimal places. But remember, we can save the x value in our calculator. If I go over here to the main screen, second mode, and press X, remember the calculator has short-term memory. So let's store this value in A. Actually, you know what? Let's store it in B. Only because it's the top limit of integrations from A to B. So I'm going to store it in B, and that way we know that it's there. But on paper, I'm going to say 0.94, what was it? 9419, we're saying, right? Our answer needs to be accurate to 3 decimal places. So in my work, I'm going to go an extra decimal just to make sure that everything's accurate to where it should be. This, my good people, is what we need. This is the integral setup that is going to find the volume of the solid. I don't know if you can even picture what the three-dimensional solid looks like, but knowing that we have cross sections that are squares that are perpendicular to the x-axis, knowing that the top function is e to the negative x squared, the bottom function is 1 minus cosine x, I can write an integral that's going to find that for me. Great. Let's figure out exactly what it is. I'm going to go back to my calculator, and I'm going to do, let's do full screen here so you can see it a little bit better. Math 9 will do the integral. I'm going to start at 0, just 1, and I'm going to go to B because that's where I saved my value, my intersection value that I found as my limit. Also, remember I saved my equations in y1 and y2, so why don't I just say alpha trace do y1 minus, oh, I need to put parentheses, don't I? Parentheses, and now let me do second trace y1 minus alpha trace, not second trace, y2 close parentheses squared, and then dx. So just a quick note. Remember, the calculator, whenever you're doing a definite integral, automatically opens a set of parentheses. So whatever you want to integrate, you have to write it exactly as you see it on your paper inside of those parentheses. So the calculator is basically telling you, hey, I'm going to find a definite integral of this thing. So put that thing in there. And if your thing involves parentheses, then you're going to have to put a parentheses yourself. So I believe this is it. Press enter. And our answer is 0.461. So this is about, let's use our approximation, 0.461. And that's it. We found the volume of that three-dimensional shape. Again, the process is pretty straightforward. Figure out what slice shape, cross-sectional shape you're dealing with. Find the area formula for that shape. Write the area function of that shape, and then take the integral of that area function in order to find the volume. That's all you need to do. We'll come back and we'll practice some more of these types of problems.